Hello everybody, this problem asks us to calculate the H3O plus concentration in each aqueous solution at 25 degrees Celsius and then classify each solution as acidic or basic. So this one isn't too complex. This is very similar to one of my other problems that I solved for in my previous videos. So just to highlight what we're given the concentration of the OH and we're asked to solve the concentration of the H3O plus, right? Alright, so there's two ways to solve this, as I said in the other videos. You can solve it using equilibrium, just by setting up Kw equals H3O plus multiplied by OH minus. But what I saw in class is people like to do the other method with pHs, and once you're in pH is stay in pH, so that's what I prefer too, so we're going to solve that one using this. So, what do? We're given the concentration of the OH, so we have to find the pOH value of that. So what you do is you do minus log of that value, which is 5.4 times 10 to the minus 4. And this value equals 3.27. Alright, so what value is that? The pH or pOH? That is a pOH value. And how do you know what it is we're solving for the minus log of the OH concentration. So that's going to give you a pOH, not a pH. So now we're asked to solve for the H3O. So what do? It's nothing too bad. You just do 14 subtracted from 3.27 will give you a pH value. What I calculated was 10.23. So now what do is you do the inverse log, which is 10 to the minus 10.23. And I calculated a number around 1.9 times 10 to the minus 11 molarity. Alright, so now we got the first part of the problem all set. We got the answer of 1.9 times 10 to the minus 11 molarity. Now, as I said in previous videos, if you want to double check yourself, you can multiply this value by this value up here. Sorry, that value down there. And that should equal something around 1.0 times 10 to the minus 14. It's not going to be exact because we have rounding, but it should be very, very close. And now you have to determine whether it's basic or acidic. So the way I solve for this is I just write both the concentrations down. You got 5.4 times 10 to the minus 4 molarity, and that is OH. Then I write this concentration down, 1.9 times 10 to the minus 11 molarity, and that is H+. Now, which one is greater, the OH or the H+ concentration? Obviously, it's going to be the OH concentration, so we can classify this solution as basic. Alright, this next problem is very similar to what we did during class. So it asks you to determine the H3O plus concentration of a 0.16 molarity solution of formic acid. So how you solve for this, you look in the back of your book on the table and you look for formic acid. And when I looked, I found formic acid is HCHO2. That is formic acid. So it says, since it states that it is an acid, we are in this constant of equilibrium. We do plus H2O, equilibrium sign, and then we do H3O plus, then you do plus CHO2 minus. And how you know that is that this was the acid, and this was the base. So this will be gaining, and this will be taking, and this will be donating. Alright, so we got that solved. So now you have to we get back to ice. I always draw it out. We Let me just move this around over here. Alright. We got ICE for initial change equilibrium. Since H2O is a liquid, we don't include it. I just cross it out so I don't confuse myself. So it says it starts with 0.16 molarity, and these will be 0, 0, as we know of our previous chapter. So as this reaction goes on, we'll lose concentration. Then we get 0.16 minus X. Over here we add X, and over here we add X. So that just equals X. Alright, so now we just got to solve for this equation. So we're just going to go on to the next page. The constant expression was Ka equals H3O plus multiplied by CHO2 divided by HCHO2, right? Alright, so also when you look in the back of the book for the formic acid, it also tells you the value for the Ka. And this value equaled 1.8 multiplied by 10 to the minus 4. And this is unitless. Alright, so now we got to go now you look back at the ICE table we did before and you just fill in the blank. So for H3O and CHO2, they are X. So I'm just going to shorten that as X squared over HCHO2, which was 0.160 minus X equals 1.8 times 10 to the minus 4. We can assume that this is insignificant, and for pretty much all the problems we'll be doing in this chapter, you can always assume a minus X or a plus X is insignificant. So now we just got to solve for X. We multiply 0.160 by this value over here, so we get X squared equals 1.8 times 10 to the minus 4. Let me fix that. Multiplied by 0.160. When you do this out, you should get a value of, when you take the square root of this value, 2.8 times 10 to the minus 5, and then you just square root that. And I calculated a value about 5.4 multiplied by 10 to the minus 3 molarity. Alright, so this is the concentration of H3O in a 1.6 molarity solution of formic acid. So the next part of the problem asks us to find the pH value of the solution. So from our mathematical formulas we're using, all we have to do is the minus log of 5.4 times 10 to the minus 3. And what does this equal? A pH of roughly 2.27. And this is similar to problem 15.32 on your chapter 5 homework number 2. So determine the percent ionization of a 0.21 molarity solution of benzoic acid. Alright, so this has another one on 15.32, I believe it was. Yeah. So you gotta look at the table in the back of your book and see what benzoic acid looks like and what the Ka value for it is. So I did that and I found that it is HC7 H5O2 plus H2O equals H3O plus C7 H5O2 minus. Remember how I found that? I said that they say that this is the acid, so this is the base. So this has to be accepting, this has to be donating, which it does, as we see here. Alright, so now what do we do? do the ice table, as always. I'm just going to shift this over a little bit so I have more room. Perfect. Alright, so let's do the ice table. Alright. As always, we can well, not as always, but liquid, H2O is a liquid, so we can just cancel that out for now so we don't get confused. We write in the given point, I'll put this in a different color, 0.12, 0, and 0. So since it's going to the right, or forward reaction, this loses concentration, so we get 0.120 minus x. This gains concentration plus x, x. Alright, now we should just write the constant expression for this. The Ka equals, where is the value? C7H5O2 multiplied by H3O plus all over H7C. H7. Oh, again. So sorry. Can't just talk about it. O2. This value equals 6.5 times 10 to the minus 5. Now, if you're confused on where I got that value, just as I found what the formula for benzoic acid looks like up here, it also tells you the Ka value down here. And this is in the back of your book. I'm not sure what exactly page, but it's very helpful. I'd print one out if I can, if I were you. Alright, so we'll go to the next page to solve this. So I copied over the constant expression for the acid. Now you just fill in what you know and what you don't know. So let's see. We discovered that HO3 plus was going to be x and C7H5O2 would be x as well. So let's just simplify that as x squared divided by 0.210 minus x equals the value of Ka, which was 6.5 times 10 to the minus 5. Again, we can assume this is insignificant, so just cross that out. Now you just solve for it. You have x squared equals divided by 0.210 equals 6.5 times 10 to the minus 5. We solve for x. Multiply this by this. So then you take the square root. So x will eventually equal 0.0036. So this is what we get as x. This is what was ionized in the reaction, this value right here. And the problem states that asks us to find the percent ionized. So all you do is you take this value, 0.00369, divided by the initial value given of 0.210. So with that said, you just take 0.00369 divided by 0.210 multiplied by 100. And this value calculates the percent ionized. And this value I calculated to be roughly 1.8%. If you guys want to double check me, make sure I'm right. And that's how you do percent ionization problems.